Now we've seen how to define functions, how to invoke functions, and especially how to understand the mechanisms by which Python keeps track of bindings of variables, both parameters of functions and other variables, in order to be able to execute the kinds of computations that we want. Let's use this to look at a slightly more interesting example and to see how having functions allows us to easily refine computations. In particular, let's go back to that idea that we had earlier of bisection search. This was going to let us try and find roots of numbers. And we can now capture that in a procedure. In fact, what we have here is something called find root 1. It looks exactly like the code that we wrote as a script, except it's now captured as a procedure. It has a number, a power, and an epsilon, and that's basically saying we're trying to find the number a such that a to the p minus x, that difference is less than epsilon. Or if you like, we're trying to find an approximation to the pth root of x. The code looks much like what we had before. The only difference is that we've got a return down here to return the answer when we want to get the answer back out. Okay, and it does this by taking initially 0 and the value x as the starting points, calling those high and low, or low and high rather, taking the midpoint as a guess, and checking to see if it's not in the right place, is it too high or too low, and using that either to search the bottom half or the top half, again taking the midpoint and using that to decide whether to search the bottom half or the top half, and to keep on going. Let's try running this. So let's go over to idle, and we're going to actually try and run find root 1. So here we go. We've got find root 1. And let's take an example. Let's find the root of 25, the square root of 25, to within a pretty good approximation. And we know the answer should be 5. Does pretty well. Let's do find root 1 of 27, and let's do the cube root of that. We know it should be 3. It's pretty good. So now let's try find root, sorry about that, let's try find root 1 of minus 27, the cube root of that, which we know should be minus 3. Oh goodness, it's hung up. What's going on? Well, let's stop this, okay, and let's go back over here and let's put in a little print statement. And let's put a print statement in right here that will just print out the current value of answer. And let's reload that. And let's go back and try this computation again. So let's see what happens if we try find root. Okay, let me stop that. So, what happened here? Why does this fail on this example? It's got caught up, obviously, in an infinite loop, and it looks like it's trying to guess at minus 27 all the way along. And we can actually see the problem. The problem is in the logic, basically, in terms of what we take as in terms of what's too big and what's too low. If we're looking between 0 and the number, and we take the mid guess, if the square of it is too small, it says we're too low and we're going to move up to the top half. But when it's a negative number, if the square of it's too small, we're going to move up to the wrong half. The logic here is wrong for negative numbers. So, how would we fix that? Well, we could try and change the logic for both ones, saying if it's negative, do one thing, if it's positive, do something else. But in fact, there's a really nice little fix, which is rather than looking over things just between 0 and x, let's basically say, look, if the number is positive, I want my low guess to be 0 and my high guess to be x. But if the number is negative, I want to reverse the logic. I'd like my low guess to be x, the negative number, and my high guess to be 0. And now I will do the search in the negative range rather than the search in the positive range. And this little change there does exactly what I'd like. While I'm at it, I'm going to clean things up. I'm going to add a little clause in here that basically says, look, if it's a negative number, don't try and take even-powered roots of that because we know we can't do it. So it's going to catch things that I don't want to try and deal with. Part of what we're seeing here is that as I test things, I ought to be thinking about a range of test cases. I started off initially just with positive numbers and was taking roots of them. And it's only when I got to a negative number that I realized I had a gap in my reasoning and I needed to think about it. Okay, with that in mind, we can go back and fix it. And in fact, I'm going to create now find root 2. I've got that over here in my Python. And if I now try find root 2 on minus 27, and I take the cube root of that, I get what I would like. That's great. Okay, so now that we've got that, let's see what else we might take roots of. Well, again, notice my tests have all been larger numbers. What about a number between 0 and 1? So let's try and find the root of 0.25, the square root of that. Looks like it's stalled again. It looks like it's stuck. What's going on? Something is not working here. So let me stop out of that and ask the question, so why does it fail in this case? Well, in some sense, the reason we can think about if we think about what bisection search is doing. So we've made these changes, but we're failing on that case. So let's think about it. When we call find root with a number between 1 and, I don't know, some big number, bisection search says take 0. We could have started with 1, but take 0 and that number and take the midpoint. Okay? And that's going to get us closer to the guess that we would like, and we're going to keep doing that. But when we call it with a fractional argument, like say 0.25, we're basically saying in our code, start with something between 0 and a quarter, and our first guess is going to be at an eighth. Ooh, that's not good, right? That's moving in the wrong direction. We know that the solution is out here somewhere, but we're going to focus only on this range, and we're going to get caught into an infinite loop where we're just going to zero down at the minus end. The original idea used the fact that the root of x was between 0 and x, but when x is fractional, the root is actually between 0 and 1. And I want to focus my search on that range. I'd like to start zeroing in only on that range. So it turns out that there's a nice, easy way to fix this code. And it simply says, change my initial guesses. So if it's a number above 1, my min will be minus 1, and the number will be whatever the original number was as the high end, and I'm going to do the right kind of search. If it's negative, it's going to be down at the other end. But if it's fractional, between minus 1 and 1, I'm going to focus the search just within that range. I've called this find root 3, and if in fact I now try that, I will find that find root 3 does the right thing. Oh, only if I type find root 3 will it? Right, so let's try that again. Find root 3 of 0.25 to and 0.001. Okay, and what about negative numbers? Oh, right, I can't take the square root of a negative number, so let's try something a little different. Find root 3, let's do it with a quarter, but let's find the cube root. And that gives me a good approximation, and if I do the same thing with minus 0.25 when I find the cube root, great. And you know what, I should go back and check some of the earlier ones I did as well, just to make sure I haven't accidentally broken things that I had done originally. So if I do 25, 2, and a small epsilon, I get the thing I'd like. And if I do, let's say minus 27 cube root, small number, again, I get the thing I'd like. So why is this advantageous? By writing a function, I make it easy to write test cases. Make it easy to check them. And it lets me, more importantly, easily go in and just fix things inside the function. If I was writing this as a script, I would have this code replicated in many places throughout my code. And if I discovered this area, I would have to find every one of those places and change it. Here, the encapsulation of the function isolates the change I have to make to just the code inside of the function. And that's really powerful. I'm going to add one last thing now to my function, something that you should do as a good programmer, and that's to add a specification. And that's the thing shown up here in a triple set of double quotes. This basically defines, as the creator of this code, what the user ought to expect. And I've given a description of it. I've said x and epsilon are either integers or floats. Power is an integer. Epsilon is positive, power is greater than or equal to 1. Those are assumptions I'm making. And if those assumptions are met, then this function should return a float that satisfies certain properties. That spec is really valuable because it lets a user, or in fact a coder, understand what the intent of this code is. And in fact, if I were to use that, when I type find root 3 into a Python shell and I open up the paren to give it a set of parameters, it will print out that information for me to remind me. The reason this is valuable is that the specifications now become a contract between the implementer and the user. it defines assumptions. What are the conditions that the implementer is assuming must be met by users of the function? It's typically constraints on the parameters, like what kind of type it should be. Sometimes it defines acceptable ranges of values. And in essence, it tells the user, if you don't satisfy these constraints, all bets are off. It often will also provide guarantees. It will specify conditions that must be met by the function, provided that it's been called in a way that satisfies the assumptions. It says, I'm going to guarantee you an answer that satisfies these conditions if you give me good inputs. And that spec lets us complete this notion of the black box. All the user needs to know is the details of the specification, and they can freely use the code wherever they would like, relying on it giving back answers that satisfy the guarantees that the user, or rather the implementer, put on them. This allows us then to sort of close the loop on functions. What do functions do? We now can create new procedures and treat them as if they were primitives. It closes a loop in which we can create new primitives to add to our code. And the functions have two really nice properties. They satisfy the property of decomposition. That says we can easily now break problems up into modules that are self-contained and that can be reused in other settings. So I might have a module that's used in a cube root function, and in a square root function, and in a quadratic root function. And that module I can easily reuse any place I would like it. The second big property we've talked about, and that's abstraction. Functions let us hide details. The user just needs to know how to use the function. It does not need to know the interior details. And that simplifies design by suppressing details that are not essential to the thinking of a user trying to do something more complicated. And so functions now are a great addition to the set of things we have in our toolbox.